you for being here. First of all, this weekly seminar, I want you to note every typo that you see or any correction or if something is not clear, because I will present this in an online meeting in 2 weeks, so it's kind of a rehearsal. It's not like a master presentation. I want that you find some mistakes, because there are plenty of them. So today I will talk about, the title is a little bit long, but quantum approximated cloning assisted density matrix exponentiation. I hope that you understand why this title after the talk. So first of all, I will review the contents of the presentations. Just briefly, what is density matrix exponentiation? We will talk about this LMR trick, which is like the cornerstone of this work. Then we will talk about imperfect cloning, in particular the biomimetic cloning. And finally, we will combine these two tools to perform this LMR protocol assisted by these biomimetic copies. So first of all, we will talk about this density matrix exponentiation. So what is density matrix exponentiation? So imagine that we have a quantum state row, and what we want to do, we want to implement this operation here. So we want to have this unitary where somehow we are loading the information contained in this quantum state row. So to do this LMR trick was proposed in this paper by Lloyd, Moseni, and Reventros. And the idea is, I have this row, I have some reference state sigma, I apply this unitary operation where this S is the swap operation, then I trace out the first register, and what I have in this second register is this desired operation, this desired evolution, up to second order in delta t. So the first question that we asked ourselves was, okay, this is what is called this LMR quantum channel acting in a quantum state sigma. So the first question is, are we able to improve this? Are we able to come up with an operation which is able to match up to third order in delta t? So the answer is that this is not possible. This protocol is optimal, so this is the best operation that you can do. So you cannot match higher order in delta t, and this was proven in this paper, Hamiltonian simulation with optimal sample complexity. So we need to find another strategy to try to improve this protocol. So the idea is, okay, now we have this LMR trick, but what if we consider time t which maybe it's not small enough to be okay with this error? So the idea is, if I have access to n copies of this quantum state, what I can do is divide this time t into time intervals of delta t and just apply this iteratively. So I have my sigma, I have one copy of rho, I apply the LMR operation, then I get another copy of rho, I apply again this operation, and I do it n times. And what I have here is, this is like the join operation. I am applying this quantum channel n times. And what I have here is this desired operation. I'm evolving rho during a time t instead of delta t, and now I'm able to control the error. I can reduce the error having access to n copies of rho. So this is equivalent of considering, if I want a fixed error, this is the number of copies that I need to obtain an error epsilon. So why this is important? This is kind of a very concrete operation, but it turns out to be a very interesting operation, this density matrix exponentiation. It's important to perform what is called principal component analysis. If I'm able to implement this operation, then I could apply the quantum phase estimation to obtain the principal components of a quantum state row, which could be like the output of some experiment. So I can extract features from a quantum state, being able to implement this operation. This was used also in this paper for also Reventros and Lloyd and Moseni, where they propose a quantum version for the support vector machine algorithm, which is one of the main algorithms in machine learning. So they need, in their approach, they need to implement this density matrix exponentiation. Also, this paper, in fact, was presented by Alex, this visitor that came 2 weeks ago, where they were doing this Bayesian deep learning on a quantum computer. At some point, they need to implement this density matrix exponentiation. Also, you could consider this rho, or you could consider Hamiltonian and try to express this Hamiltonian as a combination of quantum states, and you could evolve your Hamiltonian by means of this density matrix exponentiation. This is what is done in this paper, where they also prove the optimality of this protocol. Also, in quantum machine learning, there are some proposals by Maria Schur, where they propose some quantum classifiers that also need this density matrix exponentiation. So this is this operation is a very particular operation, but it's widely used in the literature, and it's the cornerstone of many fault-tolerant quantum algorithms. Because, for example, these two are fault-tolerant quantum algorithms. So we were asking, is there room for improvement? We know that it's optimal, but maybe we are able to still improve it. So if we consider this is the target operation, I want to evolve my quantum state sigma using rho as a Hamiltonian during a time t. This would be like the approximation that we are doing. So we somehow quantify the difference between these two. This is what we were using during this work, the norm one of the difference between these two applications to quantify the error. This is called like the error of this LMR protocol, having n copies of rho, and we know that is upper bounded by this quantity. But the idea is, okay, we know that we cannot match higher orders, but here this means that here there is something. There's something multiplying this term, and it results that we have this, the norm of these operations, of these matrices, density matrices, accompanying this term. So the idea is, okay, I cannot remove this contribution, but maybe we can reduce this contribution. Maybe we can find a better operation or a better strategy to reduce this norm, because this norm can range a wide, this can be very small or very large, and maybe you can reduce orders of magnitude the error of this protocol. So what we tried, we first tried in fact in my master thesis, we tried to find another operation. Remember that for this trick we are using the exponential of the swap. So we asked ourselves, are we able to find another operation instead of this swap, another Hamiltonian that reduces this norm? And the answer is that no, this protocol is not only optimal in the asymptotic limit, it's optimal also in this particular case if we want to reduce this norm. So we know that we cannot perfectly clone rho. We need copies of rho, but we cannot clone this quantum state perfectly. But what about considering some imperfect cloning? We know that there are different approaches to perform imperfect cloning. There are different cloning machines. So we will consider a particular case, which is the biomimetic cloning. So the biomimetic cloning was not proposed in this paper, but was extended in this paper, and this is what we use in this work. So imagine that we have n original copies, which are expressed in this way. Now we choose an observable, and we perform the cloning in the basis of this observable. So we have an observable. This observable has an eigenbasis, and we use this information to perform the cloning. This is my biomimetic cloning machine, which has as input the original copies and the basis of some observable, and what this creates is n k-entangled biomimetic copies. So now I'm not creating independent copies because this is forbidden by the non-cloning theorem, but I have some kind of imperfect copies, a set of imperfect copies. What this cloning machine is doing, this biomimetic cloning machine, denoted by this O sub C, what this does is this clones the statistics associated to an observable. So basically, if we have rho, I perform a measurement, I measure some observable on this, and this is equivalent to have these copies of the quantum, or two biomimetic copies, and measure the observable in one of them. So this and this is the same. This is why this is called cloning. So we are cloning the statistics associated to some observable. And I emphasize that to perform this operation, what I need is to choose a basis. And what we choose is the basis of some observable. So in our case, we will consider the eigenbasis of rho as we will consider rho as the observable. So we will need the eigenbasis of rho to implement this cloning machine. So basically, we start by this form of rho. This is diagonal in the rho eigenbasis, and we need some register which will contain the copy of rho. So first of all, we apply this change of basis. This is changing from the computational basis to the eigenbasis of rho. So we need to be able to implement this change of basis. I mean, I emphasize this. If this is very complicated to implement, this makes no sense to try to improve this protocol in this way. So then we apply this operation, and then we undo the change of basis. So this is what is the cloning machine. This also this is the full cloning machine, which is the setup is quite simple. So after this, what we have is we have changed from this eigenbasis to the computational basis. Then we apply this U sub C, which basically is just replicating the information with a cascade of C nodes. This is like copying the information in the computational basis. So after this operation, what I have is I have replicated this information in the second register. And after this, I undo the change of basis, and what I have complete is that I started from this quantum state and some state initializing the zero state, and we end up with this couple of biomimetic copies. So we are kind of perturbing the state. I have a pure copy of rho, and using the biomimetic cloning machine, I'm kind of making these copies. I mean, these are not clean copies, these are not perfect copies, so the question is if this is worth it to do it. So acting k times on this, what we obtain is that we are replicating these elements of the basis of rho. So this is just a formal definition, because after that we will use this. So just for notation, we can apply this k times to create a chi biomimetic copies from a single rho. So, okay, now we have seen the density matrix exponentiation, why this is important, the LMR trick. We have seen what is the imperfect cloning that we are using, the biomimetic cloning, and then we are going to join both of them to try to find a combined protocol. So we have the LMR protocol. We know that this is asymptotically optimal. We know that we cannot find a better operation than this S. We also have this biomimetic cloning machine. So we are able, from one row, we can create chi imperfect copies, but we need that this change of basis to be easy to implement. For example, considering some local bases, which are common choices for Hamiltonians or for quantum states. So we could consider local or semi-local bases, which are easy to implement, and in this case, this will make sense. So given n copies of rho, we want to implement this operation. We know that the error is of this form, so we want to simulate a time t. What we were doing with the LMR is having these n copies. We are splitting the time interval into n intervals of time delta t. But now what we are doing is from each original copy of rho, we will create chi biomimetic ones, and we will split these time intervals into this delta t will be this capital delta t divided by this k. So we are splitting the time intervals now using this biomimetic copies. So this is the main question. Is it worth disturbing the original copies, which are somehow perfect, to create chi biomimetics copies from each row? So this could lead to better results, or I'm just obtaining worse results doing this. So basically, having one row, we will apply this biomimetic cloning machine to obtain chi biomimetic copies from this row, and then we will apply this is the same architecture as before. From a single row, I obtain k, and I apply this LMR protocol k times. Okay, so it's the same as before, but now we are doing this for smaller time intervals because we are obtaining more copies from this cloning machine. So we will consider the limit where the number of biomimetic copies that I create from a single one is infinity. So it makes sense to consider this limit. I'm sorry, this is not very clear, but This is how this operation converges with the number of biometric copies. So it makes sense to consider an infinite number of copies because we can go very quickly to the convergence regime of this operation. In fact, this converges with 1 over k. So it makes sense to consider this limit for the analytical calculations, and we define a combined operation. So we consider the limit in which we are applying this T sub k, which is just this operation, which comes from obtain a row, create chi biomimetic copies, and apply the LMR protocol to each one of these copies. Then I consider the limit in which chi tends to infinity, just for simplicity in the analytical calculations. And then I do it n times, because I will not have only a single copy of row, I have n copies of row. So this is the combined operation, and just as before, I have my target operation. Now I have this biomimetic protocol, this LMR combined with the biomimetic protocol. I want to quantify this error. This will be the error. This is defined in this way. I have n copies, and I create nk copies, because from each one of the n copies, I'm creating k copies, k biomimetic copies. And this is what is obtained after computing this difference. So if you remember, when we were doing this, the question that we asked ourselves is, are we able to reduce this norm? So now what we have, instead of this norm, we have this norm, which could be similar to you, could seem similar to you, but we will see how this is reducing the error. But the dependency is the same. We know that we cannot reduce the order of the LMR protocol because it's optimal, but we have obtained a quantum channel which gives you this norm instead of the previous one. So we can quantify the improvement of our protocol by calculating like the quotient of these two errors. So having n copies, I can just apply the LMR, or I can consider this combined protocol, and the advantage that we can get from our protocol will be quantified by this quotient. So it's just the second order term, or this norm is quantifying me the error of each one of the approaches. So this is defined as Q1 because we are considering the norm 1, and this is important, as you will see now. So I want performance guarantees. I want to really know if this is worth it or this is better always. So what we do is, we studied the single qubit case as the first case, and we were able to prove that the minimum advantage using this is 2. We can reduce the number of needed original copies by 2, or we can reduce the error by 2. You can choose the statement, but we found that the case that collapses this norm is the maximally mixed state of rho. So for the single qubit case, the minimum of this quotient is 2, so the minimum enhancement is like reduce the error by half, and this corresponds to a very particular case of the single qubit case. For the general case, we proved for the norm 2 that this is always greater or equal than 2, and we conjecture the same because we did a lot of numerical simulations to ensure that this is the same for the norm 1. We struggle a lot with this norm, with the norm 1, but we only were able to prove this for this norm 2. So, okay, this is nice. So you are telling me that you can always obtain better results. The smallest advantage is to reduce the error by half, but I would like to see, in general, which is the advantage of using this. So we took a particular example, which corresponds to take this row highly mixed and sigma low rank. So highly mixed means that the eigenvalues of rho will be between 0 and 4 divided by the dimension of the system, and just this condition for the rank of sigma, just to have some example to try to do analytical calculations. And what we found is that the improvement, this Q1, which is quantifying me the improvement of our protocol, scales with the dimension of the system. So for highly mixed rho, I can find that the improvement that I'm obtaining using this combined protocol over the original protocol is proportional to the dimension. So I mean, this is a good, we are reducing the resources considerably in this, using this approach. But okay, this is a very particular example. We want to see on average which is the improvement of our protocol. So we perform an average Q1, so we plot this Q1, I don't remember, I think it was like 100,000 random density matrices for each number of qubits, and what we see is that actually the mean is linear with the dimension, so really on average we are really obtaining this exponential improvement with the size of the system. So we can somehow analytically prove this exponential behavior. So we have our quotient, and we have a very nice result in this paper, distinguishability of generic quantum states. What is telling me is that the eigenvalues of a random density matrix are distributed according to the Marchenko-Pastur distribution, and are supported, this distribution is supported between 0 and 4 divided by d, which is the same case as the particular example that we consider. So on average, this tends to a maximally mixed state. This density matrices tends to the maximally mixed state, which is the particular case that we consider. So we can prove this expression, which is greater or equal to something proportional to the dimension. And here we have some norm, which is the difference between two density matrices. And in this paper, they also show that this tends to a constant. So here we have a constant, and here we have the dimension. So somehow with these results, we are able to prove that the average advantage, the average Q1 is greater or equal, grows with the dimension of the system. So just to show a little bit some particular cases, we consider like the best case for 4 qubits, which corresponds to this one. So the resolution is not the best one, but this horizontal line, imagine, we have n original copies. So I apply the perfect LMR protocol. This is the error that we obtain applying the original protocol. Now, from each of these original copies, I create chi-biomimetic ones. So I am growing the number of biomimetic copies that I'm doing. So if I stay with the the usual LMR protocol, this is the error that I can get. Obviously, this is a flat line because it does nothing with the number of biomimetic copies. But if I let the system, if I let to create biomimetic copies, this is how I can reduce the error. Okay? So basically, I can do the same for the worst case. And what we find is this. And basically, this quotient, this Q1, is the relation between this value and this value. I take this value because we are considering the limit in which k tends to infinity, so I take a value where this curve has converged. So this Q1 is just this quotient. And just, I can show, just to emphasize these results, here is the same plot, but now I'm adding two extra lines. So imagine that instead of having n original copies, now I consider that I have n times k original copies, which these are a lot of more resources. And I apply the perfect LMR protocol. This is this curve, which is, goes to 0. So this is the LMR protocol with n chi perfect copies. This is the biomimetic protocol. This is our protocol, and here in this case, the same. So this is the perfect LMR protocol with a lot of more resources, and this is this line which comes very close to this not fair scenario, comes very close to this. I mean, I want to emphasize that this is not a fair comparison, because we in our protocol we start by n original copies, and we are comparing this with n times k original copies. So the tendency is quite close to this LMR protocol with ideal resources. So basically with this I end up the presentation. I will just put three main conclusions for this talk. So this density metric exponentiation, which is the cornerstone of a lot of quantum algorithms, can be enhanced. I emphasize I need to be fair. We require to have some easy to implement change of basis because we are cloning in the raw eigenbasis. We need to be able to implement this. On average, this enhancement using this combined protocol scales with the dimension of the system. And finally, using this imperfect cloning, there are a lot of quantum protocols that have as a resource copies of a quantum state. So we pave the way to try to use this kind of imperfect cloning techniques to these protocols, because maybe these protocols can be enhanced using imperfect cloning. So that's it for this presentation. So if you have some questions or comments.
It's like I was in the scalability, there was like a normal data. That's the one on later you say you need the norm two.
Yeah.
Why do you need the norm two?
I mean, no, we don't need it. I mean, we work with the norm one because it's the one that is used by the authors in all the papers. But trying to find analytical bounds for this norm was very difficult, and we only were able to find analytical bounds with the norm two. So the norm one, we are able to find these bounds on average. But if we want to find the bound for any case, we were only able to do it for the norm two. But this result on average, which is like this works for the norm one. I mean, we are using result for the norm one, but this is on average, not for any case. So the idea was to find if we were able to find a case which is below which is below the reducing the error by half. I mean, but we conjecture that in norm one it's not possible to find any case.
Okay, you say you have a representation first. I really like the representation of this training. You can see it, make it much.
Yeah, but I mean, take into account that, yeah, I agree with you. I didn't expect this projector is, I mean, it's
still with small these. And you have a lot of wide space, you can optimize.
okay.
The size of the thing, all this length.
Yeah.
But I like your this.
Yeah, okay. Yeah, it was basically because this will be an online presentation, and I was like looking at the screen and seeing that this was okay for this, but maybe for a classroom is not optimal, yeah, the size of this. Okay.
Then, when you say that you have to be easy to implement, you say you have to analyze, no? You have to analyze.
I mean, so you have to diagonal. I mean, maybe you don't know rho, because rho can be an unknown state. In fact, it makes sense when rho is unknown. But maybe there is the output of some experiment that you know which is the eigenbasis. For example, I mean, it's diagonal in the computational basis, so it's diagonal. And the idea is that I need to implement this change of basis. So I can know which is the eigenbasis, but I need to be able to implement the unitary. I need to find a way to construct this unitary that changes the basis. So it's not only that I need to know the eigenbasis, it's also that I need to be able to implement this unitary.
Because
Efficiently, because
the thing that you are searching for advantage that scale inside, but like to be fair, I know that you're saying that to be fair, if you grow the size, it's going to be harder to find the basis and also to like this advantage happens to be it's like somehow with the
you need to know, I mean, you need to know, because in fact, for me, it makes no sense to need to diagonalize rho, because if you know the eigenbasis and you know the eigenvalues of rho, you could construct directly the exponential of the. I mean, we don't need this protocol to implement exponentiation of rho. So this is kind of for experiments where you know the basis of the quantum state, but if you need to diagonalize rho, I mean, it's not. It makes more sense.
And in the finally, when you are in the error, you say that when you have like a physical software behind them, in the first, well, here you can see, like here, like this is like the error, like this part of the error thing. It's no, I don't know the same structure.
I mean, it's the same structure, but it comes from a completely different. I mean,
But finally, in order to say that you are not optimizing the DD.
no. And yeah, I don't remember the answer for this question, but it was one of the very first questions that came to my mind and that we discussed with Mikkel. I will reach you with the answer because I mean it's not the same. I mean it has the same structure, but it's just a coincidence, not because of the structure.
This is the error that gives this not like this square that this comes from the joint paper.
Yeah.
But then you are okay. We can.
Yeah, I mean, yeah, from the light paper they only give like the bound because this is order t squared over n. But as this cannot be improved asymptotically, we look for the dependency on this error. And it turns out to be that the intuition is that here in the numerator you have first order in the density matrices, and here you have second order. So you are multiplying density matrices, and as the eigenvalues need to be normalized, by multiplying them, you are obtaining this. This is kind of to get the intuition why of this exponential scaling with the dimension, because we have this second order in the denominator. Yeah.
Okay, all right.
I was curious, maybe you commented, I don't know, if you have some intuition of something similar could be done using the universal.
Yeah, we tried, in fact, but the universal cloning, so this cloning machine, what does is, this perfectly clones some states, but the price to pay is that you are like doing very bad cloning for another quantum states. And the universal cloning performs a uniform cloning. So you can clone a single qubit with fidelity 5/6, but the scaling with the number of copies and with the size of the system is very bad. I mean, this 5/6 is for a single qubit, but if you want to obtain more copies, the scaling is, I think, when it was like exponential. I mean, this decreases with, and also with the size of the system. If you consider cloning 2 qubits, you also have a very bad scaling. So this result is just optimal for a single qubit. So here that we want to grow up the size of the system and to create many copies is not, it makes no sense to consider this cloning machine in this case.
And I also have a suggestion or a complaint. I think that has to be detailed, but it really stuck in my head. I noticed two pronouns K, K, and Kai.
Yeah.
But I think you are seeing the same thing.
Yes.
I think be careful with that because at some point confused.
Yeah. No, in fact, it's very important. K's presentation is like one of the main words.
Okay.
Thanks. Javi, no creas.
Yeah, I was going to say several things. First, norm 1 and 2 are, I guess, use norms or certain norms.
Right. You know it, right?
Yeah.
Certain.
I will include the
Okay.
in the slide.
Okay.
I will split slide 21 into several ones. I mean,
You mean in this slide 21, no?
yeah. And I think that we could go even like a little bit further with like the distribution of the eigenvalues and maybe explain that a little bit more.
Okay.
Enough time.
Okay. Yeah, because this.
So I'll go to this because it's like the key of it's like the key of the result of like the average case. And also, I don't know if you have like a slide just for answering in case like someone asks you, okay, do you have any copies? what about measuring, retrieving information about the values and preparing stuff?
Yeah, I mean, I have not time to prepare this backup slide, but my intention is to have it for the.
Yeah, I really like it. Really like it.
Yeah, I know. Well, yeah.
And also maybe like the previous one, the previous slide, like
No, this is the 21. Yes.
yeah, everything was and it was like pretty tight at the very end when you like
Joder.
yeah, when you gave like the particular example for this, it's like okay, this is like pretty small. It's like quite important. So maybe-
It's quite important because it's connected with the average case. Yeah. Maybe this could be also repeated in the next slide.
Yeah.
Yeah. Okay.
The other thing is that what is T2?
What is?
T2.
Yeah.
You can reduce it, but
I say that this one denoted that we are working with not one, but maybe I should repeat when I go through Q2 that this is because now this is
that it's there and you never.
okay. Yeah, this is important. I will highlight with an arrow or something.
There is also an error in the next line.
In the next, yeah. Yes. Well,
This is when you go there, it's normally false. Q1 is not like this. It's the average Q1.
yeah, it's the average. This is. I didn't know how to write this formally.
No.
Okay. Yeah, this is the average. Yeah. I try to solve this putting average.
Yeah.
As I said.
When you say average, what means average you can do it in very different ways. So you have to write what is the distribution that you are taking.
Okay, I will write that this is the uniformly higher distribution of. Okay.
First, inequality is for the average or for a typical.
The first inequality is for the particular case before. This is why I don't know how to. I mean, this inequality. Yes, it's for a row which contains its eigenvalues between 0 and 4 over d. We know that on average, the distribution of the eigenvalues tends to this particular case. This is why it's a little bit difficult to formalize this.
Yeah,
Because,
no space to see.
Yes.
okay.
I don't see anything.
No, yeah. Yeah.
I mean, most of the blocks, I don't see anything. I don't see a plot, I don't see that.
I know. Obviously, when I was doing this, I was able to see everything, but I didn't expect this. Yes, it's true.
But you need
Maybe I can.
that green in the you need like a good screen
Think that no one will see this in
Maybe I can split this slide into two to talk about the average and. Okay.
Also, there is another error.
Slide 4.
You don't want to implement because here suddenly.
Yeah, appears the T. I saw during the presentation.
So you want to implement, you have one mistake sigma, another one mistake SO4, sigma, and one implement sigma.
Yeah, but yes, it's true that you want to evolve. You need this sigma to, but the literature is also present, like saying that I want to implement this operation, this unitary. Then I apply to a quantum state sigma. It's true that I will have this sigma dagger, but I don't know if it's worth it to put in this way.
I don't know, because in the next time.
Yeah, in the next time.
This one appears to sigma from
Yes.
nobody knows.
So I want to implement this unitary. This is but okay. I will try to make this.
Do something. Connect one with
Yes. Okay.
You are saying that Q1 is the error.
No, it's Q1 is
Is the
what we define to quantify the improvement. Yeah.
It's the way to quantify the advantage. But this is completely unfair. Because essentially the cost, the computational cost of one and the other is different.
yeah, it's different, but the point here is that the resources that you have, I mean, you don't have access to more perfect copies, but maybe you are able to construct this operation.
It's also
Yeah?
and patience is also a result.
It depends on I mean, it depends on if you want accuracy, you can do it. Obviously, this is a more complex scheme, this is obvious, but I don't know how could I say this. I mean, you could help me. Yeah,
We also said, made a statement that on the master thesis, it was possible to find that into the code. It is possible. And you must in general. There is no operation that is, can be used to any possible state. But
Yeah.
you have information.
this is, but this comes to your mind because you know about the whole work. This,
It's very possible row or single, which is just saying. So you have 5 weeks, so you can cancel the square term.
No, he was looking for this an operation that is in S, which is the swap. Operation that is better from this removing the delta is what.
Yeah.
There is no that operation for every possible.
Okay, but for each row, there is one such operation.
Yes, for yes, families.
And there is one reason rows,
This depends on the operation depends on.
but those families or not are not rows that are diagonalized in the same basis. No.
You can eliminate the first, second, all of them.
You can eliminate all others.
Because they commit in one.
You can be convincing one, no?
If they are diagonals, you can diagonalize them in the same way.
No, but the family is of row. So if you find an operation S that only depends on the basis of row,
yeah, but no, it was not the case. There were a lot of conditions. Not only that. Okay.
I think very common for each other.
Yes, yes. Okay.